Hello dear students, welcome you all. Well, in this lecture, I am going to discuss about the square wave generator by using operational amplifier. Generator using operational amplifier. Clear? So, in this entire lecture, I am going to discuss how we can use an operational amplifier to design a square wave generator. Now, we know a square wave generator, we can say it as a stable multivibrator, because we know the astable multivibrator do the same thing. What it do? It generates continuous square waves without any external input signal. Right? It continuously switch between two unstable states by itself. Right? So that is astable multivibrator. Oh, so here, whatever circuit we are going to discuss, we can say that it is a kind of astable multivibrator. Right? So we are going to make the use of operational amplifier it. At the end, we will see the waveform that is generated by this circuit. So first of all, I will draw the circuit diagram of a square wave generator, right? So for it, again the same thing, we will start from a operational amplifier, right? So this is operational amplifier. This is the output terminal. The resistance path. This is for capacitor, right? This is the circuit. This is for load resistance, taking output, right? These are two supply voltage for the op amp, right? No, ground. This. Now I am going to induce various components in the circuit, right? So it is, I will say, feedback resistor R, right? Uh, this is again a feedback resistor, that is R2, and this is R1. This plus B.Sc minus VEE, right? This is plus, this is minus, this is load resistor, this is output, right? Now I have applied a capacitor here. This is capacitor. This is virtual ground. Again here it is ground, right? Now this is gain of this basic amplifier A. Right. Now, this is the circuit C. You can see the circuit diagram for the square wave generator. Now, you can see here, this is basically a modification of a comparator circuit, or even I can say it is the modification of a Smith trigger. Right. Here, we are using capacitor instead of using the input signal. This is the only difference. Right. So I can say this is basically a comparator circuit, right? Now I have two, inputs nodes. This is one and this is a two, right? Let this is node one, this is node two. So what this circuit will do? This circuit will, every time compare, two inputs, the input appearing at point, 1 and input appearing at point 2, and it will generate output voltage according to that. The output voltage will be either in, positive B saturation, or it will be in a negative V saturation. It will depend upon the condition whether, the input at this terminal is higher or input at this terminal is higher. Now, what is the input at this terminal? The input at this terminal is obviously the voltage appearing at the capacitor, right? And what is the input at this terminal? Input at this terminal is obviously the voltage appearing across this resistor R1. And what is the voltage appearing across R1? We can calculate it if I assume that current I is flowing in this way, right? I, then it goes toward this side I, because nearly zero current go toward this side. So by using the same thing, I can say if I call that voltage, the voltage appearing at this point or this point, B threshold, then that will be equal to what? It will be equal to R1 into V output divided by R1 plus R2. Clear? Now, this is what is the output sorry, voltage appearing at this node 2. Now we know output can be in either positive saturation or in a negative saturation. So according to that, I will have B upper threshold, clear, is equal to R1 B plus saturation divided by R1 plus R2. Similarly, when there is negative saturation voltage, I'll call lower threshold R1 upon R1 plus R2, right, into B negative saturation. So these are the two voltages, right, that will appear as this terminal. In the case when the output voltage is either positive saturation and either it is in the negative saturation, right? Now we will see what is the voltage appearing at this node 1. So as I told you, the voltage appearing across capacitor will be equal to the voltage appearing at this node 1, right? Now let's see how this comparison will work, right? Suppose when we switched on the circuit, then initially B output can be either in positive saturation or a negative saturation. We also know that the gain of the op-amp is very, very high. So even a very minute signal appearing at the input will force it into the saturation. So suppose initially B output was in a positive saturation, right? Let B output was in a positive saturation, right? It is in a plus B saturation. What does it mean? It means at that time the voltage appearing at this node is equal to what? It is equal to B upper threshold. Clear? Obviously, right? Now when the output is in plus V saturation, right, means it is positive, obviously, then what will be the effect of this plus V saturation on this capacitor? The capacitor will start charging in this way, current will start flowing in this way, and it will start charging toward plus V saturation with this polarity. Clear? Current is going in this way, and the capacitor will get charged in this way, right? Positive here, negative here. It will try to charge up to plus V saturation, but when the voltage on the capacitor reaches this value, right? Up to that point of time, the voltage at this terminal was higher and the output was in plus V saturation. What when the voltage at the capacitor, I can say BC, is greater than B upper threshold, right? This value, then what will be the effect? Now the voltage appearing at the inverting terminal becomes higher than this. The output will swing to the negative saturation. Now it will switch to immediately to the negative saturation. So what will be the output now? It will go to the negative V saturation, right? So at very that time the output will get inverted from positive saturation to negative saturation. And when it happens, what will be the effect on the voltage appearing at this node? You can see from here, when it is in negative saturation, the output will the not output but the threshold voltage at this terminal will become this one. Now the voltage appearing at this terminal is now B lower threshold, right? Now we see that the voltage at node 2 becomes B lower threshold at that time. But what is the effect of this negative V saturation on the voltage appearing at the capacitor, right? Because now here it is negative saturation, negative here. What will be the effect? The effect will, this capacitor will start discharging, right? Now the capacitor is discharging, it will completely discharge, and then after it will again start charging, but now it will start charging toward B negative saturation, toward this polarity. It means now in this case the polarity, or you can say the charge on these plates will get reversed. I will have now, I can say I will have now positive, positive, and a negative, 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 negative. So you can see when the output changes from plus V saturation to minus V saturation, the capacitor first of all discharge in this way by flowing current from here to here, and then after it again charges, but now it charges with its polarity this one. Clear? Now when the capacitor is charging with this polarity, it will keep on charging. What? When the voltage across capacitor will go more negative than B lower threshold. Clear? Then what will be the effect? Now the voltage appearing at this terminal, this is higher than this value. Again, the output will swing to the positive V saturation. So this will complete one cycle. So this charging and discharging of the capacitor will continue, and the output of this circuit will continuously fluctuate, or I can say change its states from plus V saturation to minus V saturation. And in this way, we will get a square wave. Now I am going to draw the waveforms of this circuit, right? That will make the things even more clearer. For it, let's take the axis. This is the output waveform I have drawn here. We will see how this output waveform is generated. Yeah, this is output waveform. Uh, Oh, even I can draw it in this way to make it very clear. What is this? This is the voltage across a capacitor. This is the waveform of the voltage across a capacitor. That's why I have taken a separate color of it to make it different. Now, right. So this is what? This is output, right? Voltage. This is what? This is voltage across a capacitor. Capacitor, right? And this is 0. This is plus B saturation. This is minus B saturation. This point here. This point here. Now this point is B upper threshold, and this point is B lower threshold that I have taken here and here. These are the two voltages. This is voltage across the capacitor, right? Right. Uh, this is time. This is voltage axis, right? So you can see from this diagram that this is the voltage across a capacitor. What we have assumed? We have assumed that initially when the time t is equal to 0, the output was in a positive saturation. So then the capacitor start charging, as I told you, toward plus V saturation. So when the voltage across capacitor at this point, it try to go beyond this upper threshold value. What will be the result? The result, the output will go to the B negative saturation. You can see here, right? So then after, first of all, the capacitor will discharge. It will become 0 at this point, and then after it will try to charge to the negative V saturation. So when the voltage across the capacitor tries to go below this point, B lower threshold, what will be the result? The result, now when this terminal voltage is less than this, again the output will swing to the positive saturation. Clear? You can see here. You can see here. So this cycle continue, right? If I consider this entire cycle from here to here as one cycle, complete cycle, then it has time period t. So it is, you can see here it is t by, right? So it is very clear from this graph that how this circuit will, freely produce continuous square waves, just like a stable multivibrator. But basically, it was a kind of comparator circuit with some modifications. Right now, we are going to drive the expression for the frequency of these square wave. Right. Obviously, the frequency will depend upon the value of different resistors and capacitor. Right. So we will drive it. Right. Expression for a frequency of a square wave, right? Now to find the frequency, we will take the help of charging and discharging of the capacitor. We know very well that the capacitor is, charging from B upper threshold to B lower threshold, then again from B lower threshold to B upper threshold, right? So this is the time, total time taken by the capacitor to go from upper threshold to lower threshold to upper threshold, and vice versa. So we will make the use of this charging and discharging of capacitor to find the expression for a frequency. We know the instantaneous voltage across capacitor B C at any time t, B C T is equal to B maximum plus bracket B initial minus B maximum into e raised to power minus t upon time constant tau. Clear? Now here BC is what? Voltage across a capacitor. B maximum is the maximum voltage up to which capacitor can charge, right? B input initial is the initial voltage of the initial voltage across the capacitor. So let's suppose we are taking from here to here. Yeah. Let the capacitor is going from a B lower threshold to B upper threshold, right? So the initial voltage is what? B lower threshold. And what is the maximum voltage that capacitor can have? It is obviously plus B saturation, right? This is the maximum voltage. Suppose at any instant, right, at any time, the time is t is equal to t1, the voltage at capacitor is equal to B upper threshold. You can see from here at this point, even you can see from here that any time t, suppose the voltage across capacitor is this is what? B upper threshold. So then for that I can modify this equation number 1. It will become B upper threshold is equal to B plus saturation. Now I will not add plus what, you can add for convenience, right? Plus B initial is what? B lower threshold minus B plus saturation into e raised to power. Now T is T1, right, upon time constant is RC, R and C. Clear? For a RC circuit. Now I can modify this equation. This equation will become minus B lower threshold minus B plus saturation into e raised to power minus T1 upon RC is equal to B upper threshold minus B I did mistake. Actually, I have taken this term toward this side and taken this term toward this side. So it will become B plus saturation minus B upper threshold. So if I further simplify this equation, e raised to power minus T1 upon RC is equal to B plus saturation minus V upper threshold divided by this value. This is negative, so I can rearrange it. It will become B plus saturation minus B lower threshold, right? Now if I take logarithm both the sides, then it will become minus T1 upon RC is equal to natural log of B plus saturation minus V upper threshold divided by B plus saturation minus V lower threshold. Clear? If I took it toward this side, then it will become T1 is equal to, so it will become T1 is equal to RC into log of E B plus saturation minus V upper threshold divided by B plus saturation minus B lower threshold. Clear? It was negative here. So if I take the negative toward this side, these terms will get inverted. So I can say T1 is equal to RC log of E B plus saturation minus V lower threshold upon B plus saturation minus V upper threshold. To adjust this negative, here I inverted these terms. Now it becomes this. This is T1. What is T1? T1 is the time going from here to here. Clear? From this B lower threshold to B upper threshold. So that same time will be taken by the capacitor in coming from here to here back. That will make it a complete cycle. You can see here, right? So the total time period of this cycle, that is one complete cycle, is equal to 2t1. So that is, so I can say now the time period for this square wave is equal to 2t1. So I can say that t is equal to 2rc log of E into B plus saturation minus V lower threshold divided by B plus saturation minus V upper threshold, right? So what is the frequency? 1 upon a time period, 1 upon a 2rc log of E into B plus saturation minus V lower threshold divided by B plus saturation minus V upper threshold. So this is the expression for the frequency of the square waves that I talk about in the beginning, right? This is the frequency of this these square waves generated by this circuit, right? This expression. So you can see like this is equation number 2, right? So you can see from here that by adjusting the value of R and C, right, I can change the frequency of the square waves. I can generate the square waves of a desired frequency. Other factors on which this frequency depend is the value of V lower threshold and V upper threshold, and on one factor these V lower threshold and V upper threshold depend, because plus saturation is a fixed value. Upper threshold and lower threshold value depend upon the value of a resistor R1 and R2. So it means in this entire circuit, by adjusting the value of R1, R2, R and C, I can generate or produce square waves of a desired frequency, right? So this is all about a square wave generator using operational amplifier, right? So this is all about it. Thank you very much.